So nobody has any questions about anything, we can go ahead and start with the workbook assignment. So I sent out an email, like this email right here, and there's 3 problems where the last problem has, there's 3 questions within it, and I was going to discuss these problems in class today. And it'll give us more of a review as of the particular topics that we covered previously in the past 2 sections. So I guess from there we can go ahead and get started. So we'll start off with page 18 from the workbook, and in particular, problem 1. So we'll start off with problem 1 from page 18 of the workbook, which gives us a rational function. And from here, the problem wants us to determine various characteristics about the function. So in particular, the domain, the intercepts, and the asymptotes, which are things that we have found before. So we're just going to do it again for this problem in particular. And so we can start off with the domain. So let me go ahead and close the door right fast. So give me a second. Sorry if that was distracting anybody. So the domain, remember the domain for any rational function is you set the denominator not equal to 0. And you solve for x. And so you can add x squared on both sides, or whichever way you do it, you should end up with x squared is not equal to 4. Just some version of that. And then that's good because we can square root both sides. Which will yield that x is not equal to plus or minus, well, the square root of 4 is 2. So if anything, that's the domain. And that'll be helpful in a bit when we get to asymptotes, as we'll see momentarily. We'll move on to the x-intercept, which remember, that always is equated to setting y is equal to 0. And so when we set y equal to 0, that means we're setting the whole function equal to 0. And by setting the whole function equal to 0, as I did in the video, as well as in some of the problems in the problem session, the way we can proceed with this is by cross multiplication. And so the good news about that, if you recall from the previous lecture or previous lectures, we're multiplying the denominator by 0, which is just simply 0. What we are left with is just that 0 is now equal to the numerator. So 0 times the denominator zeroes out the denominator. And so now it's relegated to factoring a simple quadratic. This is x plus, x minus. And in particular, it looks like x plus 4, x minus 3, nothing too crazy. And so we get that x is negative 4 and positive 3. So we get 2 x-intercepts. Okay, so from here, we can go ahead and find the y-intercepts, where we set x equal to 0. So when we set x equal to 0, then so this one's generally the easier one. Just simply set all the x's equal to 0. So we then get negative 12 divided by 4, which is simply negative 3. So that is the domain, the x-intercept, and the y-intercept. So from here, we can go ahead and proceed with the asymptotes. I'll go ahead and put the asymptotes right here. We'll start off with the vertical asymptote, because this one is very much associated with what the domain tells us. In fact, the rule of thumb that I provided before was that the majority of the time, the domain and the vertical asymptote will be virtually the same, with the exception that we just change from a not equal sign to an equal sign. So notice it's the exact same thing. The domain, in the majority of cases for rational functions, will tell us the vertical asymptotes. That's pretty much true for the majority of the problems. In fact, I haven't seen one yet where it's not true. You might have seen it already in the homework, but this is true the majority of the time. And so from here, we can also go ahead and find the horizontal asymptote. It's the horizontal asymptote. So hopefully you recall from the lecture that this is found by comparing the degrees of the numerator and the denominator together from the rational function. So I'm just going to rewrite the function. Now you might notice this rational function is not in standard form. And when I say standard form, what I mean is, well, the numerator is in standard form by itself, but the denominator is not. And sometimes, and in fact, it'll help us in a bit here to put both of these in standard form. So I'm just going to change the denominator slightly. So now the denominator as a polynomial is in standard form, as in the dominant term is in the front, followed by the slowly decreasing exponent terms, or the descending exponent terms. And from here, now we know what the leading terms are, and figuring out the degree is a pretty straightforward process. The degree of the numerator and the denominator, as we can see, are both 2. Because that is the exponent of the leading term. And so remember what that tells us. Since the degrees are equal, then that means that the horizontal asymptote is the ratio of the leading coefficients. So what are the leading coefficients? Well, this is exactly why we put everything in standard form. Because now coefficient just means number, just the number in front. So now that we put everything in standard form, we can see that the ratio is 1 divided by -1, which is simply -1. So the final answer for the horizontal asymptote, because they generally want an equation, is y is equal to that -1 value. So that is the horizontal, that's the equation of the horizontal asymptote. Y is equal to -1. And from here, we have now answered all the individual parts. And we can go ahead and graph the function, graph the rational function. And there is a graph on your workbook page. It goes by 2s, 4, 6, 8, 10, 12, and so on and so forth like that. So what we can go ahead and start off doing is, I'll go through these one by one. So the domain, that was really helpful for the vertical asymptotes. So let's go ahead and plot down the vertical asymptotes first, which we found the vertical asymptotes to be plus or minus 2. So since this graph goes by 2s, then these would go right here. X is equal to 2, and X is equal to negative 2. And those are the two vertical asymptotes. And we can also additionally go ahead and plot the horizontal asymptote, which is negative 1. So this one's going to be right here, right underneath the x-axis. So those are all the asymptotes. And from here, we can additionally go ahead and plot any intercepts that we have found. So we found two x-intercepts, the x-intercepts being negative 4 and positive 3. So negative 4 would be over here, and positive 3 would be right here. We do also have a y-intercept of negative 3, which that can be plotted right here. Since it's a y-intercept, it has to be on the y-axis. So from here, we know that the graph has to converge or get really close to the asymptote, but on which side of the horizontal asymptote? That's what the points help us determine. So this point being over here tells us that we are above the horizontal asymptote. And then the point being down here tells us that we are below the horizontal asymptote. And then the point being right here tells us we are again above the horizontal asymptote. And then that's how you would construct the graph. Now, this is a little bit more gratuitous of a process in comparison to your homework in my math lab, considering on my math lab, the graph is a multiple choice thing, and you have to choose the correct one. So again, you don't, as you all found out, you don't have to be this vigorous about deriving the structure and various characteristics of the graph. It does help you determine which graph is correct, but and it is helpful, but don't expect to have to construct graphs like this. Again, for the third test, you don't have to send me any scratch work, but it is good to know from an intuitive standpoint how to derive these various components, as it'll make picking the correct graph, say on a homework or on the test, much easier. But other than that, this is the graph for the function. And does anyone have any questions about this before I move on? If not, let's move on to the next problem. So we're moving on to problem 2 on page 18, which same directions, different function. So it says here's a new function, which is equal to 3x minus 6 divided by 16 minus x squared. And we'll just go ahead and do for this problem the same as we did before. We'll start off with the domain. So the domain, once again, we set the denominator not equal to 0. And we would end up getting that x squared is not equal to 16 in some way, shape, or form. You will end up getting this. And like we did before, we square root both sides. We get that x is not equal to plus or minus 4. So if anything, we have that for the domain, which, as we saw before, will be helpful for finding asymptotes in a bit. We'll move on to the x-intercept, which again, it means setting the function or y equal to 0. So whenever we do that, we can cross multiply like we did before. And once again, we have the denominator times 0, which is just 0, which leaves us with the numerator equal to 0. And it gives us a simple linear equation that we can solve for, add 6 on both sides, and then divide by 3. Just get that x is 2. So if anything, we have the x-intercept. We can also go ahead and find the y-intercept right fast by setting x equal to 0. And so from here, all the x's zero out, and we are left with negative 6 divided by 16, or negative 3 over 8. One second. Sorry about that. Okay, so we have the intercepts and the domain, and from here we can go ahead and figure out the asymptotes. So again, there's 2 asymptotes that we can figure out. One of them we can figure out fairly quickly. So we'll start off with the vertical asymptote. And once again, the vertical asymptote and the domain are pretty much inherently related for the majority of the problems. It will also be true here. Just notice the slight variation with the not equal sign to an equal sign. And that's it. And the horizontal asymptote, as I mentioned before, this has to deal with the degree of the numerator and the denominator and how they compare with one another. So what we can go ahead and do is write it in standard form, as sometimes that helps us determine the degree a little bit more easily. But as we can see, the degree of the numerator is 1, and the degree of the denominator is 2. As it, again, it represents the largest exponent from the numerator and the denominator, respectively. And so, as we can see, the degree of the denominator is larger. So whenever the degree of the denominator is larger, then actually the horizontal asymptote is y is equal to 0. That's it. No other number, just y is equal to 0 every time. This will happen every time the largest exponent of the denominator is larger than the largest exponent of the numerator. It's always just y is equal to 0 every time. And so from there, from here, we can move forward to, now we can graph everything. Again, the graph is separated by intervals of 2. And so I'll go ahead and start off with the vertical asymptotes. We found 2 vertical asymptotes at +4 and -4. So since these go by increments of 2, then they would go here and here. And the horizontal asymptote goes, well, it says that y is equal to 0. Because we found it right here. So now we've plotted all of the various asymptotes. We have 3 of them. And so now we can go ahead and plot any intercepts we may have, which we have 2. The x-intercept is x is equal to 2. So notice in an interesting turn of events, we have an intercept on the horizontal asymptote. Now, horizontal asymptotes can be intersected. It doesn't happen too often, but it does happen. So I just wanted to let you, make you all aware of that you can intersect a horizontal asymptote. You can't intersect a vertical one, but you can intersect a horizontal one. And the reason why it's a little bit more technical than this class requires, but it does happen. So if you see that happening, it is a possibility. And this is an example of such a possibility right here. So, so we have the x-intercept here on the asymptote, and the y-intercept was -3/8. So -3/8, that would be a little bit below the horizontal asymptote. Now the question is, how do we fill in the remaining pieces? Because if anything, these 2 dots have to be connected. And the graph also has to slowly converge or get really, really close to the various asymptotes. But on which sides? That's what we need to figure out. Now, if anything, this graph in the middle, this graph has to go upwards here and go downwards here. Because if there were any modifications to those directions, then we would have had another x-intercept, which we would have computationally, we would have found that. But we do not have any more x-intercepts, which means that graph cannot cross the x-axis anymore. So this has to be the logical shape of the middle part of the function. But now there's these gaps on the left and the right, over here and over here. And the question is, well, on each one of those sides, where does the graph happen at? On the top or on the bottom? So where does the graph happen at? And that's what we need to figure out. That's That's what makes this problem a little bit more challenging than, say, a MyMathLab problem, where you just think about the multiple choice. So here, what we would need to do is pick a test point, which is generally what you would need to do in this situation in MyMathLab. But at least in MyMathLab, they have the graphs laid out for you. Now, when I say a test point is some x value that you plug in. Say we plug in x is equal to 6, and whatever the output is will tell us which side of the horizontal asymptote the graph's going to go on. So if we do pick 6, we're plugging this into the function, into the very function in the beginning that we had. And so 3 times 6 is 18. 18 minus 6 is 12. 16 minus 36, that's negative 20, I believe. So we get a negative number. In other words, we get a very small negative number, which means that the dot is going to go down here somewhere. And that's all we need, because we know that the graph has to trace these asymptotes like this. That test point tells us, does that shape happen below the horizontal asymptote or above? And what we found is that it happens below, because we found a negative number. So it didn't even matter what value the negative number was. It really doesn't matter at all. And that's on the right side of the graph. On the very far left side, over here, so over here, same idea. We pick negative 6 because that's the number that's to the left of negative 4. And once we compute all of this, see in the numerator, we get negative 18 minus 6, that's negative 24. And then we get 16 minus 36 again, which is just negative 20. And so let's see, this is positive 6 over 5, I believe. And so we get a positive number, which means that this shape will be happening above the x-axis. So that's how test points can help you determine, well, distinguish between different graphs if you have a multiple choice selection. You can use test points like I did here. You pick a random point you pick a random x value that will represent a point you need to distinguish between. And once you plug it back into the function, it'll tell you this, all right, hey, this is where the point goes exactly. Your graph better agree with this point that you just found. But this would be the graph for this rational function here for problem 2. So does anyone have any questions before I move on to page 19 of the workbook? And I'll answer your question. I will specify on your question in a bit about the sign chart. Does anyone have any questions for this? If not, let's go ahead and move on. We'll move on to page 19. And problem 1, as you may notice, has 3 various problems within it. So we'll start off with 1A. And these So now we're not looking at rational equalities and graphing rational functions. We're looking at polynomial and rational inequalities. So you'll see the abundance of greater than signs, less than signs, all the inequality symbols. And we'll talk about how to solve those, which will be consistent with my lecture video on this. So from here, the first thing, so in regards to the sign charts, so you might have noticed in the homework that some of the questions made you provide the sign charts. Some of them just said, state the answer, whatever it may be. And the truth of the matter, so if they do ask you a question that asks you, if they ask you a question that makes you provide the sign charts, then unfortunately you do have to provide it. Otherwise, if it just says state the answer with no other accompanying work, then you may do that as well. So that's pretty much, and this is something I will discuss more so in Wednesday's review session, the types of problems that you will be expected to know and the types of formatting that may accompany said problems. So this will be something that I can elaborate on more so during Wednesday's Unit 3 review session. So hopefully that gives you a more, more clear answer for the time being. Okay, so all right, so let's keep going to so 1A. Well, the first thing we want to do is we want to move everything to the same side, because the goal of all of these, we want to factor polynomial and rational inequalities as much as we can. This is so we can find the zeros of the expression. And so in order to find the zeros of the expression, we need to, of course, factor, but that means everything needs to be on the same side. So let's go ahead and move the 12x over, which means I would subtract 12x on both sides, and we get exactly here. And now that everything's on the same side, we can go ahead and factor as much as we can. And the first thing you may notice is that all of these terms have an x in common. So we can factor out the x to get x squared minus 4x minus 12 is greater than 0. So that's the first step, because they all had an x in common. So notice after I factored out the x is still there. And now each subsequent term now has one less of an x value. And from here, we can go ahead and factor this quadratic to factor this even further. So this is x minus 6, x plus 2. And notice the greater than 0, that just keeps following the whole, for each following step. That greater than sign keeps following everything, as we will use it later. But with the factorization, negative 6 times positive 2 is negative 12, and then their sum is negative 4. So now we have factored the problem as much as we can, which is very good, because now we can figure out the zeros really easily. The zeros from this problem, each factor gives us a different zero. So each factor gives us a different 0. And from here, as you may remember from the video, we use this information by constructing the number line. Or if you do it a different way, I mean, there's a bunch of different ways that people do this problem. If you YouTube somebody else doing this and you like their method more, you're more than welcome to use whichever method you'd like. I personally use the number line method, and you know, it's just a preference. If you don't use this one, there's another one you found, but by all means use that one, as long as you get the right answer. It doesn't matter. And notice I put all the numbers in order. So I put -2 first because that's the smallest, and then 0, and then 6. And so in my lecture video for this, I believe I included 2 methods for how to fill in the blanks here. One of the more predominant method was you pick test points from each region. And so if you use the test point method, you would pick a test point from each particular region. So here, just any number less than -2, -3 would be fine. And here between -2 and 0, so -1, and you could pick 1 and then 7. And so what you would do with all of these is you would plug each one of these into the most simplified factored part of your inequality for your x values. Now, there was also another method that I described, which included using multiplicities. And so with the multiplicity method, well, of course, you get the same conclusion, but if you can identify the multiplicities, then you only have to pick one test point no matter what. Now for this problem, what I'm going to go ahead and do is talk about the multiplicity way, and for the next problem, I'll use the test point way, just to give a nice diversity, and you can pick whichever one you like more. But if you want to use the test point method, well, there's your test points, and you can go from there. If you use the multiplicity method, then all you need is just one test point. And I normally like to pick the largest one. But the multiplicity method, we need to find the multiplicity of each one of these numbers. So I'm going to put underneath each one of these numbers, m is equal, m, of course, being multiplicity. So the multiplicity of, say, -2, well, -2 comes from this factor. What's the exponent of that factor? It's 1. And then for 0, 0 comes from this factor. And what's the exponent of that factor? It's just 1. And then 6 comes from this middle factor here. The exponent of it is 1. So what does that tell us? Remember, in odd multiplicity, odd, just 1, 3, 5, 7, 9, 11, so on. Odd multiplicities mean we will cross. So all of these have odd multiplicities. So the graph will cross at each one of these values. So we'll apply that momentarily. The test point of 7 we need to plug 7 into the function or into the inequality and see what kind of value we get. So we're going to plug this in. And I'm going to plug this into the most recent, most factored part. That generally tells us the most condensed amount of information. So that's going to be 7, 7 minus 6, 7 plus 2. And if we plug all of that in, This is just 7 times 9, which is 63, which is a positive number. So when we plug in 7, we get a positive number. And so additionally, so the reason why we only need one test point is because to go from this segment here, in fact, I'll do this in red. In order to cross over to this segment over here, well, to move over, we have to cross. And by crossing, that means that the sign will automatically alternate. So notice the plus sign becomes a minus sign. So notice we did not even need to pick a test point. By moving over a point or a 0 that crosses, we automatically know to alternate the sign. And again, if we go over to the next interval, past the 0, 0 says to cross, so the sign will alternate. And then to go to the last one, once again it crosses, which means the sign will alternate. So notice, we were able to do all of that without having to pick test points. I mean, you can pick test points and you will get those exact signs. And if you want to do it that way, you're more than welcome to. This method is really nice whenever you have a lot of test points, which you might notice in part C, for example. In part C, you will have four zeros, which means you would have 5 test points. So that's a lot. But for maybe part B, where you're only going to have what ends up being 2 zeros and 3 test points, that might be a little bit more manageable. In any case, now we have the signs of the various intervals. So from here, we can figure out, okay, well, do we include the zeros in this problem? We do not include the zeros because the sign does not allow zeros to be included. It's only greater than 0. So if anything, there's an open circle at each 0. We do not include them, which means in our final answer, we're going to be using all parentheses. And since it is greater than 0 that we're looking for, we need to only select the ones that are positive, because the inequality is telling us we strictly want greater than 0. So that means all of those intervals that we just highlighted, we're going to go ahead and jot those down as our solution set. So we said that this interval is good from -2 to 0. And we're going to use a union because we also said this interval was good. That interval starts at 6 and ends at positive infinity. And that is our answer. So does anyone have any questions about this problem? If not, we can go ahead and move on to the next problem, or next part, 1b. Which says 9 minus x squared is less than 0. And the first thing we need to do is, well, factor this as much as we can. So in order to factor this, well, really, I want to put this in standard form. In the last problem, all we had to do is subtract 12x on both sides. For this problem, to put this in standard form, not only do we need to swap the terms, to put the dominant term first, but we also need the dominant term to be a positive number. Generally, that's very helpful when we factor. So by simply adding x squared on both sides and subtracting 9 on both sides, now we have 0 on the left side, and on the right side, we just have x squared minus 9. And so notice we ultimately moved everything to the right side. And the reason why we did that is now the leading term is positive, which means this is in standard form. And once we have it in standard form, we can go ahead and factor. In fact, you might even notice the factorization here is a difference of 2 squares. Just like that. Difference of 2 squares. And the reason why we factor is so we can figure out the zeros really easily. So each factor gives us a different 0. So from here, now that we have the zeros, like we did before, put it on a number line. And I like to put them in order. Just so happens I listed them in order. So -3 and 3. And for this one, I'm going to go ahead and find the 3 test points. If you wanted to go about this problem using multiplicities, you would find that the multiplicity is 1, multiplicity is 1, and they cross, which means your signs would alternate each time you cross over the 0. But just to offer a diversity of methods, I'll just pick a test point from each one. So here we could pick -4. So that one, all we need is a number less than -3. Here we could pick 0. Here we can pick +4. So -4, we just plug in -4 in for each x. So -4 plus 3, -4 minus 3. And so that gives us +7, I believe. Which is a positive number. And we just keep going. We have 2 more test points. So that was the first one. See, and by knowing crossing or touching behavior, I already know that each one's going to cross. So I already know that it's going to be negative and positive because they have to alternate. But if you use the test points, you'll figure out these values the exact same way, which equals -9, which is a negative number. So then that's why you would put the negative here, which is right above the test point of 0. And then finally, 4, the test point of 4. So it's 4 plus 3, 4 minus 3, which is simply 7. So we get a positive number when we plug in 4, so that's why there's a plus sign up here. And so from here, now that we have the signs, which regions give us plus and which ones give us minus, and also in my video, I believe I suggest scratching out the test points because they do end up being big distractions. So I like to just scratch them out because your final answer is going to depend on these values, not your test points. Test points are only temporary values. Once you use them, you toss them immediately because they tend to end up, screwing up your final answer. So here, this problem is wanting us to find values greater than 0. So we're looking for positive values, positive regions. So that's why this region on the far left would be good, and this region on the far right would be good. Now again, we ask ourselves, do we include the zeros themselves? And for the same logic as the previous part, we do not include the zeros. That's why I'm putting open circles here. We do not include these zeros because there is not an equal to part in our inequality symbol. If there was, then we would use brackets everywhere, but we don't have to. We're going to be using parentheses to exclude those zeros. And so for each one of these, we can go ahead and contribute all of this towards our solution set. Looks like this region is one of the regions we highlighted, which goes from -infinity to -3. Then a union, because we have this region on the far right, from 3 to infinity. So this is our final answer. So does anyone have any questions about 1B? If not, we can move on to the last part, part C. Let's go ahead and do that. Move on to part 1C. What 1C states, they want us to find the solution set for this rational inequality. And so here, we have a rational inequality as opposed to a polynomial inequality, because rational implies the existence of a fraction somewhere. So obviously this is rational. This is a ratio of a polynomial divided by a polynomial, or quotient. So that's exactly what a rational function is. So we'll end up finding that the process is fairly similar. But, well, the first thing we would ask ourselves is, all right, we need to factor this rational function as much as possible. The way you factor a rational function, well, you factor the polynomial on the top and the one on the bottom. Now, the way you factor those, as you all are aware, the workbook tends to give slightly more complicated problems. So you would maybe use the AC method or guess and check for factoring. And I'm going, for the sake of time, I'm going to just state what the factorizations are. Let's see, let me make sure. So that's 5 times -1 is -5, 5x minus 2x is 3x, cool. And then 3x is a plus, there's an x and a plus, pretty sure it's 2 and 6. 6 times 2 is 12, 6, okay, cool. So I'm going to leave the how to factor up to you all. But once you do factor, you would get these factorizations for both the numerator and the denominator. So what's interesting, though, is that the second part, what we just factored to, is not fully factored. So this part right here is not fully factored because there's one slight exception. again, this is much trickier than the homework questions. It's not fully factored, so the numerator is fully factored, but the denominator is not, because the 3x plus 6, that can be factored. We can factor a 3 out. So what happens when we factor out a 3? Then we get x plus 2. But you might notice that we already have an x plus 2 in the denominator. And now we just found another x plus 2. So that's why I'm going to square it. So once we factored the 3 out of here, then we're left with an x plus 2 that we can combine with this x plus 2, which gives us, well, 2 x plus 2s, or x plus 2 squared. And then from here, really, we can not factor, but simplify very slightly by multiplying both sides by 3. Which gets rid of this 3 down here in the denominator. And then what we finally have, our final simplified form, is exactly this. This is the fully factored form. Again, much more difficult than what you would expect on a homework question, but that's, how the workbook generally goes. And so from here, we can proceed with determining the zeros. So the zeros come from each factor. So what would the zero of, say, this factor be? And so that factor, well, what is the zero for that one? It's negative 5 over 2. That's how you find the zeros. So it's negative 5 over 2 for that one. This one's much easier. It's just positive 1. And then for the one in the denominator, it's negative 2. So we have 3 zeros, which we can now go ahead and put on a number line. So I'll put these in order of which one's the smallest, which does end up being negative 5 over 2, because that is negative 2.5, which is smaller than negative 2. And then we have positive 1. So from here, so if you use the test point method, I'm going to use the multiplicity method. But if you were to use the test point method, you could pick test points of negative 3. This one right here is kind of the tricky one. You would have to pick negative 2.25, because that is a number in between negative 2 and negative 2.5. If you were to use the test point method. Here you could pick 0, and here you could pick 2. So again, I'm not going to use this method, but I wanted to give you all an idea. If you prefer to use the test point method, here's the test points you could use. I'm going to use the multiplicity method, which means that I only need to pick one test point, and I need to figure out the multiplicities of everything else. So the test point I'm going to pick is the 2 that I have on the far right side. And I'm going to go ahead and figure out the multiplicities of each one of these zeros. So we'll start off with the negative 5 over 2. The negative 5 over 2 comes from this factor that I underlined in blue. Its exponent is understood to be 1. we'll move on to the -2. -2 comes from this bottom factor, which has an exponent of 2. So that factor has an exponent of 2. So we'll get to that in a second. And then the 1 comes from this factor right here, which has an understood exponent of 1. And so finally, what this means, so the odd ones are crosses. So this one's cross and this one's cross, but the even one in the middle will be touch. So we haven't seen an example of touch quite yet in the workbook examples. So now let's go ahead and plug in the test point of x is equal to 2. So we plug 2 into every single x value in the most recent simplified factored form. So this will be, it seems to be 9 divided by 16, which is a positive number. Now for the multiplicity thing, if you chose all of your multiplicities correctly and you determined crossing or touching correctly, and each time you go over, then...
Oh, okay. Oh, I didn't know you were teaching.
Oh, I got 10 more minutes.
Oh, okay. I didn't know anybody was in here.
Oh, yeah. Sorry about that. So from here, when we cross over, by identifying everything correctly, since crossing over here or moving over means we cross, then the sign has to alternate. So that's how I know that this is a minus without picking a test point. And so now the sort of new idea here is by moving over to this next one, since it says touch, then we do not alternate. We do not alternate this time. So that means the minus sign will repeat as a minus sign, because that's what it means to touch. It means we do not alternate the sign. But then to go to the next one, since we are moving to an interval where we have to cross, then the sign will alternate, and then we do get a plus sign. And so that's a way of figuring out, again, using the multiplicities, it's a very compact way of determining which intervals are positive versus which ones that are negative. Now the question is, which ones do we need? Which ones are we picking, the positive ones or the negative ones? And using the sign, it says we want things greater than 0. So naturally, we want the ones that correspond to a plus sign, which is why I'm picking the far ones on either side. So the final thing to address is what happens to the zeros. Now it says here that we include the zeros, but that doesn't mean that everything is a perfect 0, so to speak. One of the zeros that we found was in the denominator. In particular, it was the -2 here. Since it happened in the denominator, that means that at -2, there's an asymptote happening, which means there's always going to be an open circle there. So we cannot equal that asymptote, but we can go ahead and fill in the zeros that we found in the numerator, because those are not asymptotes. So in our final answer, this interval we highlighted, which is -∞ to -5/2. And then on the far right over here, so we use a union. This is 1 to +∞. since the arrow tells us we keep going in that direction. And that would be the final answer there. That actually concludes the workbook assignment. So if nobody has any questions up to this point, then that's all I have for today. The next class period is going to be the Unit 3 assessment review. If you haven't done so already, please watch the video for composite and inverse functions, composite one-to-one and inverse functions. And I'll answer any questions for the next few minutes if you have any. Other than that, have a good day.